Okay, so maybe we can start now. So on behalf of the Alice India collaboration, first I welcome you all to the second talk of the Alice India webinar series. So it is a great pleasure and privilege today to have with us Professor Abhijit Majumder from Wayne State University, Detroit, Michigan, USA, as our speaker. On behalf of the Alice India collaboration and all participants, I convey my sincere gratitude to Professor Abhijit for finding time for us and accepting our request. And of course, for joining from USA so early in the morning in an election day. So Professor Abhijit Majumder is a well-known physicist in the field of physics, and to this audience, I don't think any formal introduction is required, but very briefly, I will say a few words about him. So, a lot of people are joining. I have to admit them. So, at present, Professor Abhijit Majumder is an associate professor in the Department of Physics and Astronomy at Wayne State University, Michigan. Professor Abhijit did his graduation in 1995 and master's in 1997 from IIT Kharagpur, India. He completed his PhD in 2002 from McGill University, Montreal, Canada. He worked at Lawrence Berkeley National Laboratory during 2002 to 2005 and at Duke University during 2005 to 2008 as a postdoctoral fellow. He worked as visiting assistant professor at Ohio State University during 2008 to 2011. And then in 2011, he joined Wayne State University as an associate professor. This is the same year when I also joined Wayne State University as a postdoc, and I got an opportunity to listen to Professor Abhijit for the first time there, and I still remember his talk. That is one of the most remembering talk for me. Professor Abhijit's research interest lies in the theory of strong nuclear force in nuclear and electron-ion collisions, particularly in the field of jets and jet quenching phenomenon in QGP. He has about 92 publications. Many of us are well aware of the JETSCAPE Collaboration, which is basically a multi-institutional interdisciplinary collaboration to develop a comprehensive theoretical software framework to study and understand the QGP via jet medium interactions. Professor Abhijit is one of the key and pioneering persons behind the formation of this collaboration, and presently he is serving as the spokesperson of this collaboration. I thank Professor Abhijit again for being with us today and invite him for this talk. So Abhijit, now you can take over. So maybe we will take all the questions in the end, and I would request everyone to keep their mic mute. So Abhijit, please.
Well, thank you, Siddharth. Thank you for such a nice and formal introduction. I think you also reminded me of that talk in 2011, and I think I'm going to bring that talk up, or some parts of that talk up today. And thank you again for taking my mind off the election, at least for a few minutes. All right, so I'm hoping everybody can see the screen. Somehow I cannot see what I'm projecting, so I'm just going to move on to the. So now you should see the second screen.
Yes.
So overview. Okay, so I wanted to talk to you today a little bit about JETSCAPE, but also in the context of determining jet transport coefficients. Especially, I want to focus on what has been for me for many years a personal approach to try and figure out the jet transport coefficient that is called Q hat. Okay, so the way the talk will go is that we will start off with some discussion on scale dependence. I'm wondering if you can see my mouse moving on the screen.
Yeah, we can see that.
Okay, good. So we'll start with some scale dependence and asymptotic freedom. Talk a little bit about the strong coupling nature of most QCD transport coefficients. And strong coupling is basically a code word for hard to calculate. Then we'll focus on jets and jet substructure. And for most of the last 20 years, my focus has been mostly on jets and jet substructure. And then we'll talk about Q hat, which is the leading jet transport coefficient. We'll discuss a little bit about the work of the JET collaboration and the continuing work now of the JETSCAPE collaboration. And spend some time on scale dependence in jets, scale dependence of the evolution of the jets, scale dependence of transport coefficients of jets, a little window into data-driven, which is now, all the rage, of course, right? Everything is about data science. So we'll discuss a little bit about the data-driven extractions of Q hat, and maybe present some hot of the press stuff over this. I'll talk a little bit about a lattice calculation of Q hat, which is something that me and my collaborators have put out recently. Whenever I talk about the JET or JETSCAPE collaboration, you'll know I'm talking about their work because in the top right-hand corner, that's that way for you, there will be an icon of the collaboration. Okay, so, and when it's not there, that means I'm talking about my own work or my own view of something. Okay. I know that's what Siddhartha is. You should ask the questions at the end, but I don't mind if you would like to interrupt me and ask a question, because it also makes this a much more realistic interaction. As you know, otherwise I'm really talking to my computer screen, and I'm not really talking to an audience. So if you have any question, I think it's fine with me if you want to just stop me and ask the question. So we're talking about QCD, and as most of you know, it is the theory of quarks and gluons. Okay, quarks, they have three kinds of strong nuclear charge or color charge, and along with quarks, there are the antiparticles, which are called anti-quarks, which carry anti-color, obviously, and that's I have this pictorial representation of these hollow circles for that. And then there are these gluons, which carry, of course, which is the force carrier, which, unlike the photon, carry what we call adjoint color, so that you can think of it as like a color and an anti-color. So the result of that is, if you think of a quark, for example, in this arrow, in this semi-Feynman diagram here, right, radiating a photon, the color of the quark obviously does not change, and the charge of the quark does not change. But when a quark radiates a gluon, right, its color changes, and the fact that the charge carrier has a color also allows gluons to scatter off other gluons. Okay, and this diagram, more than all the others, is responsible for what we call asymptotic freedom. That is, this coupling here tends to weaken, and weaken very dramatically as you increase the momentum scale of the interaction. Okay, so here you see a range just from 1 GeV to about 1,000 GeV. That's about a TeV. And the coupling has weakened from about 0.5 all the way down to about 0.1. So a factor of 5 reduction. Okay. So this property, of course, is well known and leads to many interesting consequences. So, for example, in deep inelastic scattering, where you take an electron and you bounce it off a proton, what the electron sees or what it bounces off in the proton depends on the scale. Okay, so in that case, of course, the scale is often called Q squared. Q squared is sort of like, if you wish, it's the momentum transfer that the electron has off the photon, and the higher the momentum transfer, the closer the electron can get to the proton. So you see this little white circle here. So imagine that you start with very, very low q square. That means the electron bounces sort of far away from the proton. Okay, so it sees a small colorless object. As you increase q square, the electron will start to get closer to the proton. Okay, and then at some point it will begin to start seeing objects or structure inside the proton. I think some part of this simulation was also there in that talk that Siddharth was referencing. As you keep increasing the q squared even further, something interesting starts to happen. I mean, initially you start to see 3 objects inside the proton, which we think of as the 3 constituent quarks. But as you increase the scale, you start noticing suddenly that there are many other objects inside the proton, right? There are antiquarks, there are gluons, okay? And this is often quantified using a quantity which we call the parton distribution function, and that's sort of plotted here. So this is the up quark distribution function, the down quark distribution function. And it's plotted as a function of the momentum carried by the quark divided by the momentum of the proton, or momentum fraction carried by the quark or gluon. You have to bear in mind that the gluon distribution is scaled down by a factor of 10. So actually it's a big number, right? And this is at a scale of about 2 GeV squared. So that I think comes down to about 1/10 of a Fermi or something. So I think if you now increase the scale even further, you get even closer to the proton. The picture does not change qualitatively, but it does change quantitatively. What ends up happening is that the gluon distribution, the C quark distributions tend to explode. So now these are being scaled down by a factor of 20. And so most of the proton at these high resolution or short distance structure of the proton is mostly gluons. Okay. All right. So, okay. What's another consequence of all of that, of course, is the consequence of asymptotic freedom, or the weakening of the coupling as you go to higher and higher scales or shorter distances. Another consequence is that the force should weaken as you increase the temperature, right? Temperature, as we know, is basically a measure of the mean momentum transfer. So that would mean that if you take a nucleus, a ground state of neutrons and protons, and just if you put it into a container and somehow heat it up, right? These will start bouncing off each other. The nucleus will destroy itself, and then other particles will start being produced. And at some temperature, you will start seeing particle excitations, for example, pions and kaons, and this is what we call a hadron gas. And if you keep increasing the temperature, at some very high temperature, we expect that we should see a quasi-free plasma of quarks and gluons. Okay. This is something that we have already seen, and it roughly happens in the range from about 50 MeV to 150 MeV. If you want that in Kelvin, it's about half of a trillion Kelvin to about 1.5 trillion Kelvin. This, I would argue, is still not completely clear that we have seen this kind of state of a real plasma of quasi-free quarks and gluons. And so I want to put a lower bound on the temperature and say maybe it happens above 600 MeV, because that is about the highest temperature we've seen in heavy ion collisions. And all of you know what heavy ion collisions are. That is our way of basically heating up matter. So I always like to show these simple little movies of where we are right now, or what our understanding is right now of heavy ion collisions. So here's one of these collisions is done by the MAD-I collaboration. That's a collaboration that sort of existed at the same time as the JET collaboration. It was really focused on statistical inferencing and making, but they made these fantastic videos. So I just want to share some of these with you. So there's a collision, and we understand that there's an initial plasma produced, which can be described by hydrodynamics, which continues to expand and cool. And at some point, when it cools down and goes into a gas of hadrons, You have a hadronic plasma, which then expands, freezes out, and then free streams to our detectors, and that's what you measure. Specifically in detectors like the ALICE detector. So here's some results from the ALICE detector, which is, of course, everybody's favorite detector. What is plotted here is the yield of hadrons in bins of transverse momentum and pseudo rapidity. And so definitions of transverse momentum and pseudo rapidity, if you're not familiar with that. And plotted, of course, also in dropping centrality, or sorry, increasing, depends what you mean, most head-on collision to almost peripheral collision. Okay. Now these are technically artificially separated, but in principle, you know, the particle production is maximum in the most head-on collision and becomes less and less and less as you go to less and less collision. Okay, so how far, you know, what is our understanding about the fluid dynamics that is used to explain all this data? So here I'm going to borrow some results from recent results from the JETSCAPE collaboration, where they were looking at several different collisions at several centralities. Especially interesting are those collisions that happen which are semi-peripheral or semi-central, where you expect to form some kind of a fireball, which has different pressure gradients in different directions, leading to anisotropic momentum being produced, or momentum distributions being produced. And this is totally sort of driven by the viscosity of the plasma, which is an input parameter, which is something you put in and then you sort of extract. These are results from the latest Bayesian analysis done by the JETSCAPE collaboration. These are plots of spectra as a function of centrality. So that's again now put down here. And plots of the different elliptic flows and PT distributions and all that. But the point I want you to get at is to just look at this plot of viscosity, shear viscosity, entropy density. These are the bounds that we've put on it. This is a very low number, which means that viscosity of the plasma is very, very low. The shear viscosity of the plasma is very low, which means if you try to relate it to, you know, your undergraduate kind of thinking about viscosity is roughly inversely proportional to the cross section in laminar flow. And so that means that the small viscosity means a very large cross section, which is another way of saying that the medium is strongly coupled. So how do you study strongly coupled media? Well, we can study the substructure of strongly interacting media. Okay. For example, all of you know that a proton is strongly interacting, but we can still study. That means that when you say something is strongly interacting, what that means is it's difficult to study it using perturbation theory. Perturbation theory is always our standards and most straightforward tool to study any system. And it's hard to do that for things like a proton, and it's hard to do that for things like a Quark-Gluon-Plasma. But we can study what we call as partonic substructure, and that's exactly what I was talking about in the deep inelastic scattering experiments, right? That at high, you cannot study the dynamics of the whole system, but by increasing resolution at one point, you could study in one small region what the quarks and gluons are doing over a very short period of time. So this is basically a high resolution or short distance study of the system. And the same is probably also true for the Quark-Gluon-Plasma. So in the case of a proton, the short distance probe was basically a high energy electron. In the case of the Quark-Gluon-Plasma, the probe is going to be jets. Now, it goes without saying that comes with several caveats. And most important of this, and I have no other way than other than just to come out and say it, jets are really complicated. Okay, so what does a jet look like? So here's my cartoon of a jet. A jet usually starts off from a very hard interaction that produces a parton, quark or gluon, which is very far off its mass shell. And so it is very unstable. So it can only travel a very short distance before it starts to decay into other particles. Being very far off its mass shell, it tends to be very small in transverse size. So that's why it's a very thin arrow. As it decays, the partons in the shower get closer and closer to their mass shell. They become less unstable. And so they can live longer. That's why the arrows are getting longer. And they get larger in size, right? Their transverse size continues to increase. Remember, size is using Heisenberg uncertainty principle. Delta X is the inverse of delta P. So as the momentum scale continues to drop, the size continues to increase. Okay, so this is if you take this object and you put it in a moving medium, okay, then first thing that will happen is that this will start to interact with the medium and start exchanging energy. And since this has a much higher energy, or jets typically have much higher energy than most of the other particles inside the Quark-Gluon-Plasma, the jet will tend to lose energy and will tend to get a little bit broadened in the medium. And by energy conservation, it will excite the medium. Okay. Some of the jet will clearly get out of the medium, some part of the jet, and it will hadronize outside. And the remaining part of the jet will partially equilibrate with the medium and partially will not, and will hadronize as the medium hadronizes. Okay, so many things happen to the jet and the energy deposited by the jet as it goes through the medium. And everything other than the leading hadrons, and by leading hadrons, what we mean is the highest energy hadrons that come from this, will be affected by what we call medium response. That is, will be affected by excitations in the medium that are correlated with the jet. And when you do any kind of jet clustering or try to catch the jet on this side, you will catch the jet. You will catch particles from the medium that are correlated to the jet. You will catch parts of the medium that are not correlated to the jet. And then, of course, you have to do some kind of subtraction to remove the ones that are not correlated. So if we just focus on those very, very high energy partons or hadrons in the medium, their modification is understood by what we call transport coefficients. So the leading one that most of you must have heard of is called Q hat. Q hat is the transverse momentum per unit length, and that is transverse to the direction in which the parton is traveling. So it tells you how it's a measure of sort of the kicks perpendicular to the direction of motion of the parton. Another one is often called E hat, which is the drag that it faces, and it slows down the parton as it goes through the medium. And there are many others, and we'll get to those in a few minutes. But let's focus on these for a while. If we go back to that talk that Siddharth was talking about, let's go back 10 years. And if I try to make a plot of Q hat as a function of some property of the medium, that plot would look like the plot that you're seeing right now. Right? There's no error. There's absolutely nothing on the plot. Because at that time, even 10 years ago, there was no universal accepted value of Q hat. There were several extractions from data, but most of them, they're all over the place, off by factors of 20, almost, or more. What people could agree upon at that time was that Q hat is definitely an intrinsic property of the medium. And if you just look at the dimensions of Q hat, momentum squared over length, then you can easily convince yourself that it dimensionally scales as energy cubed or temperature cubed. So it would make sense to present it as a dimensionless ratio, which is Q hat over temperature cubed as a function of temperature. And so my temperature range basically goes from like 100 MeV, where we know there's no more plasma for sure, up to maybe a GeV of temperature. Everybody agreed that there should be a transition between the confined and the deconfined phase. Everybody expected to be small in the confined phase and large in the deconfined phase. And I already said this, we will need to scale it with some intrinsic quantity. For example, temperature cubed or entropy density or something in any kind of realistic simulation. So right off the bat, you could ask, well, what if I try to calculate it using perturbation theory? And by perturbation theory, what I mean is perturbation theory for the whole medium, which we already, we're not sure that that's a good idea because we're not sure if perturbation theory applies. But perturbation theory here means hard thermal loop or HTL perturbation theory, which I'm sort of diagrammatically showing up here. So there's the yellow line is let's say is a parton in the jet, scattering off partons in the medium, which are these red objects, and you see these blobs on these lines, and the blobs basically mean there's a summation of all of these loops into these blobs. And if you follow this method of calculation, this is kind of the formula for Q hat that you would get. It has this characteristic log of energy times temperature divided by the Debye mass, and the Debye mass is also given as temperature squared. So forget all the other factors. So it really is energy over temperature. So ET over T squared is energy over temperature. And I've made a plot now where the energy is set to 100 GeV. There is one thing you don't know in this plot, which is what is the scale of alpha S? What is the alpha S, as we said, depends on the scale. That was the plot I started out with. And so I've put in a range of scales from about 2 pi times temperature to 4 pi times temperature, and that's what these bands are. The lower band is for a purely glue plasma. That's exactly what these diagrams are showing you. No quarks at all in the plasma. And the green band is for a full Quark-Gluon-Plasma in equilibrium that has 3 flavors of quarks. The lower end is the higher scale, and the upper end is the lower scale. I think that's what I wanted to say. Anyhow, the point here is that since it's energy over temperature, as you drop the temperature, HCl predictions have this characteristic curve upward. And that's essentially comes from this log of energy over temperature. Okay, so even though so the alpha S, of course, is becoming stronger because there is the scale, the temperature scale is dropping, but also there's this log E over temperature, which gives this upward turn as you go down to lower temperature. I should stop at some point, maybe ask if people have questions, and if people can still hear me.
No, Abhijit, we can hear you, no problem. Maybe I can ask one question just for continuation.
Yes, sir.
Is that does it make your Q hat is Q square? It's so does it make any sense to talk about Q hat in vacuum?
No.
No.
No. So it really means that you have to have something exchanged with the part. So you are right to say that if I just look at a jet, where did I have that? You are right to say, now I have to go back through this animation again, that when a parton splits, even in vacuum, like in this picture, every split, it generates transverse momentum, right? So the parton does gain transverse momentum, even in vacuum, just by splitting, right? But Q hat is meant to be the extra split, the extra transverse momentum that comes purely from scattering. Okay.
Okay. Okay.
So if the medium goes away, then basically Q hat goes away.
Okay.
Okay. Should I go on?
Yeah, please.
Okay. All right. So the next question is perturbation theory valid? I mean, we used it just to calculate, use that formula. Is it valid at these temperatures? The plot I made was with mu between 2 pi t to 4 pi t. And if you put down temperature about 250 MeV, then 2 pi t is about 1.5 GeV, roughly speaking. And so if you look on this plot now again of how alpha S runs with Q, 1.5 GeV is about there. So the alpha S in that range is somewhere between 0.4 and 0.5. So it's a big, it's not really small. Perturbation theory works when alpha S is small. It really works really well when you're out here, and it becomes progressively bad as you go down and down and down. Okay. So it's not clear if perturbation theory is applicable at these temperatures, but we can try to get Q hat using jet or leading hadron energy loss. Okay, and that really was what everybody was doing even 10 years ago, is to look specifically only at leading hadron nuclear modification factor. And you can criticize that, and we'll get to that in a few minutes. And that really means that you look at a collision of two nuclei. In this, I call them A and B. They collide, they make a plasma, and then there's all of these two jets that sort of go through this medium and lose energy. Generally speaking, the nuclear modification factor, in case you're not familiar, is the yield of an object, which we will call N.
Can I have a question?
Yes.
So you said that this perturbative theory will work there because that means that PT is very high or small.
I said perturbation theory may not work because the scale, or the temperature scale, is not high enough.
Okay. So when I want to just know whether this PT is small. So since the lattice, basically that is the region of non-perturbative region, right?
PT of what? Let me ask that question first. What are we talking about? PT of the jet or PT in the medium?
PT of the, okay, jet, you can say the jet or particle production, right?
So for the jet, the PT is large enough to apply perturbation theory. But the problem is that, if I go back to this diagram, the jets, so people get, there's a lot of confusion of what PT means, right? So when you say the jet PT, that is the PT in that direction, in the direction in which this yellow line is going. Q hat is momentum that is perpendicular to this. Okay, so the transverse momentum that is the source of Q hat is perpendicular to the direction in which the jet is going. And this transverse momentum that is in Q hat or is from the medium is at a temperature where perturbation theory may not work. For the jet, which is at a much higher PT, but going in this direction, for that perturbation theory works. It's not clear if perpendicular direction to that, there is enough temperature for perturbation theory to work. Makes sense?
Yeah.
Okay.
So can I just have one follow-up question? So
sure.
When we say that this perturbation theory will be applicable after certain PT range, some PT cutoff on jet. So is there any particular value of that, or it is sort of 2 GeV, 1 GeV, or where one can start this perturbation theory strictly?
So never below 1 GeV. Okay. And most people will tell you that about 1.5, is the absolute limit, right? Below this.
No, but that you're talking about the leading particle, right? Not of jet PT. This
is for a single particle inside the jet.
So 1 G doesn't make any sense anyway. So yeah, that's yeah, leading produced particles. Yes, correct.
Mhm.
Yeah,
Can
go
I answer your
ahead.
question to that? Okay, so we are now looking at leading hadron nuclear modification factor, or RAA, and as I was saying, so most of you already know what this is. It's the yield in some range of impact parameters, so from low impact parameter to large impact parameter divided by the same yield in a PP collision, scaled by the number of expected nucleon-nucleon collisions. So all of you know this. I just want to point out what goes into this, any of these calculations. There's an integration over impact parameter, integration over location of where this scattering that produces the jets take place, integration over momenta of the two incoming quarks or gluons that enter the hard scattering. There's a probability of getting a quark in nucleus A, probability of getting a quark in nucleus B. There's a scattering cross section where the two partons will scatter and they'll go out as partons 3 and 4. And then there's a probability of energy loss, okay, or modification of the outgoing partons or shower, and finally the fragmentation of that into hadrons. In all of these things, the one that is really sensitive to the medium profile is this energy loss term or modification term, and that is technically proportional, linearly proportional to Q hat, which can be a function of T cubed or temperature cubed, or a function of the entropy density. Okay, so obviously this depends on the space-time profile of the fluid dynamical simulation. And so let me now take you to the about, now we're about 6 years from ago, about 2014, and there was a serious attempt made at that time in the JET collaboration, icon over there, to try and extract Q hat, where they insisted that all of the calculations would use the same hydro simulation. So the hydro simulation is the same, but every other aspect in that formula that I showed you was different between the different calculations. So here are calculations from CU JET. These are calculations by Xing and Wang in Berkeley. These are my calculations. These are calculations from the Amy group at McGill, all explaining the leading hadron, central leading hadron suppression at RIC and at LHC, using a combination of ALICE and CMS data. And many of you have seen this plot from the JET collaboration. It points out all the different values of Q hat that are obtained by all these different models. Let me just back up 1 second and show you what I mean by all these different models. That's why I had this formula. In all the different models, these terms up here are all different, right? The only thing that is same is the hydro simulation that gives you the Q hat profile. And everything else is different. So when you apply that to data and you try to extract the Q hat, you get a different value of Q hat. But they all noticed that you needed one normalization for RIC and a lower normalization for the LHC. So here are all these different bands from all the different models. Some of them use this HTL formula that we just talked about, right? The perturbative formula, and you can easily find them because they have this upward turn. Okay? This pink line and these all are using the HTL formula, but when you're doing phenomenology, you have to sort of cut it off at the point where you think that the medium has transitioned from Quark-Gluon-Plasma to a hadron gas. So you do that by hand. And other models often use entropy density to scale and don't use the HTL formula, and they have a natural turn off as you go down. So that's the blue line or the red line here. Have this natural turn off because they're scaled with some other property in the medium. They're not using the HTL formula. Anyhow, you take all of this and we put it on our little plot. And so here is the normalization at RIC. Here's the normalization at the LHC. Now I've put them on this one plot compared to the HTL results, and lo and behold, they're not so bad, okay, compared to the HTL result. What one has to be very careful about interpreting this result is that this point is the normalization at RIC. This point is the normalization at the LHC. Between the highest temperature in the LHC and the highest temperature of RIC, there's a 20% difference.
Can you explain what do you mean by normalization here?
So you have to fit, right? So Q hat, when you say, what we do is, I wish there was a way to fast. So Q hat is proportional or scales with either temperature cubed or entropy density.
Okay.
Okay, so Q hat is some number times temperature cubed or some number times entropy density. What is that number?
So Q hat is a momentum, right?
No, it's momentum
Q
square.
hat squared per unit length.
Square.
Yeah.
Yes, momentum squared per unit length is Q hat. And so it is, you have to scale it with temperature cubed or entropy density and the scaling factor. Or you could say that I scale it with the HTL relation that we have. Okay, and then again, what is the factor for that? And that factor depends on what model you are using, and it depends upon whether you are applying it to LHC or to RIC.
Okay.
Turns out RIC has a higher normalization than LHC. Okay, and this is a big mystery, which I've spent most of the last 6 years worrying about.
Okay.
Two things to keep in mind. Sorry, go ahead.
Go ahead. No problem.
Okay. So two things to keep in mind. The highest temperature at reached at the LHC is only 20% higher than the highest temperature reached at RIC. Whereas if you looked at those plots carefully, the maximum momentum of the leading hadron is almost at LHC is 5 times. It's goes to up to 100 GeV, whereas RIG only goes up to 20 GeV. So there's a factor of 5 difference there. This is how it should have been interpreted, but this is not how most of the community interpreted this plot. I think many of you have seen plots like this, which say that this means that Q hat over T cubed has this kind of non-monotonic or hump-like structure between the deconfined and the confined phase. So it doesn't just generally come down like that, but it might do something like this. And I don't think that's right, okay? Because if there was a hump like this, you would have seen it in the centrality dependence of the RAA, you would have seen it in the azimuthal anisotropy or the V2 of the leading hadrons. And I took those same calculations that were used for the JET collaboration plot, and I tried to see, if I just did centrality dependence without putting in any such bump, right? Would there be a systematic failure? And there wasn't a systematic failure. This is at LHC. This is the V2 at the LHC, and you think they would definitely show up in the V2, and it doesn't seem to show up in the V2. This is the V2 at RIC, which of course is, the fit is not as good as the LHC. The error bars are bigger, but still there's no real systematic indication that there is this big bump as you go down in temperature. But over the last years, a lot has changed, okay? Because remember, we had all these different models that we used. And what we've come to understand now, and I'm speeding up because I noticed that the time is running out, all of these different approaches to energy loss are really valid in different epochs of the jet. That is, at different times in the life of the jet. So a complete description would require all of these approaches to be applied in tandem, sort of one after the other, depending on where they are, right? And how the jets interact with the medium, of course, depends on the temperature of the medium, but you now have to broaden that perspective and imagine that it could also depend on the energy of the jet, it could depend on the scale of the parton, it could depend on a medium scale, other than Q hat or temperature. So what our picture now is that when you start out with a jet, it starts initially in this, what we call the radiation dominated region. So this is the early part of the jet, right? Where it's it has a very high scale, it's very off shell. In this region, it has mostly radiation. Even if it did not have a medium, it would be radiating like crazy because it's very far off its mass shell. And it has occasional scattering. as it goes through the medium. So that's why I call it the radiation dominated regime. In this regime, it would obviously sample the medium at very high scale. So there's an echo. Can somebody mute their microphone? Thank you. And this is often the theory that part of the theory that describes this often is called the higher twist or the GLV, and in Monte Carlo language, these are Monte Carlos like matter and Yagem quantify this phase. Then there is the lower virtuality or the high energy part of the jet. That would be, the highest energy part in the later shower, and this is in a region which I call scattering dominated. What that means is that you have few radiations now, or few emissions, but many scatterings. The scale of the parton has really come down and is now at this medium scale called Q hat times tau, where tau is the lifetime of the parton. And this is the energy loss theory, which is described using terms like BDMPS or AMI, and in Monte Carlo language, that would be LBT or Martini or Joule. And of course, then there could be a low virtuality and low energy part. And for this, there is no perturbation theory at all. Most of these could be absorbed by the medium. They cannot be described by perturbation theory. There are lots of models that go out that talk about what it is. Remember, the scale of the parton is the same as the scale of the medium, and some people use ADS-CFT. And this really is a picture where you have no substructure at all because there's no hard scale in this problem. Okay, so Yagem had one incorporation of the ADS-CFT. Another model that uses it now a lot is called the hybrid model that has Isia, and then it uses ADS-CFT drag. So our grand picture now is that you have this jet, okay? Some part of it is within the BDMPS kind of phase. Some part of it is in this higher twist kind of phase. There's a transition region, which is not well understood yet. Some part of the jet is in the strong coupling phase. If you have an expanding QGP, of course, it will depend, how this transition happens will depend upon where you are in the expanding QGP. And there's energy thermalization. Some of the energy that goes out will start to thermalize with the medium. And all of this is going to happen. And in the end, there's going to be a hadronization of all of this up. Okay? So you will have transport coefficients like Q hat, and you could keep going in that series because Q hat, remember, was PT squared over L. You could go to the fourth power as well. It could be, you could think of other higher transport coefficients like Q hat 4, which would be the fourth moment if you want. That's one way of going. Along with drag, you could have the straggling factor or E2 hat, which is the fluctuation in the energy exchange between the parton and the medium, and you go down this series. And all of these transport coefficients really tell you about how the medium changes the jet. But they're now, if you want to talk about the whole jet, then you also need transport coefficients that tell you how the jet changes the medium. Right? So the jet deposits energy in the medium, and this energy then thermalizes and becomes a source term in the medium. So these are other separate transport coefficients which connect between the jet and the hydro. Typically, the way we do it nowadays is using a method called recoil, where you sample a medium region with a Boltzmann distribution. You take out one of these partons, you let the jet parton scatter off of it, which may or may not produce an emission. The outgoing parton is the original direction of the parton, of course, is changed, right? And what you have now is a hole traveling in the medium. So you keep track of this hole. And the outgoing parton, after it's scattered in the medium, that again now becomes like another jet parton and can have more scattering in the medium, producing more recoil partons and more holes. So the holes are these dashed lines. That's one way of doing it. You could do it another way called broadening, where everything just gets multiple soft diffused kicks as it goes through the medium. Or there could be drags, that you could have strings dragging down all the jets. So you could do many different things now. And the way to really resolve all of these things systematically is to use what I call an event generator framework. And that is what JETSCAPE sort of is. It's not an event generator. It is a framework where you can go in and change any part of the generator using your input, if that's what you like, and still use all the other components. Okay, so JETSCAPE has two parts. One is the event generator part, and the other is the statistical emulation and comparison with data part. So let me just focus on the event generator part. Each of these boxes is a piece of code that is open source that you can just go to our website and download. You get the whole thing. Okay, and then you just have to learn how to attach one of these modules. If you want to write one of your own, you're welcome to do that. You can take out a module and put in a new one. And you have an initial state module. You will have a free streaming module. You will have a PCA module that does the hard scattering. You will have modules that do energy loss, at high virtuality, low virtuality. You will have a fluid dynamic simulation in there, all connected together, right? You have a hadronic cascade, and even now we also have hybrid hadronization, which includes recombination. So the idea of the framework is that it's an event generator that you can change to whatever you want. And then you can use our statistical tools to then compare with data and see how well that is. So let me now quickly go over, I have about 5 minutes more. Siddharth, how much more time do I have?
Yeah, we can continue. Yes, we have, because we still, yeah. Yeah, we
Okay,
start.
so
Maybe 10 minutes more if you want. So.
Okay, so let me now, when you have this kind of an elaborate framework now, one other thing I have to tell you is how you hadronize in JETSCAPE. So what we do is when you have a jet that goes out, you want to have the same setup of hadronization, at least for the hard sector, in AA collisions as in PP collisions. So once the jet comes out of the medium, it should hadronize in vacuum the same way as it does in AA as in PP. So what we do is we look at the color of the originating parton. We make an anti-parton and send it down the beamline, because nothing is being detected in that direction. And then we attach a string, and then let the string break in PCA. And there are multiple different ways of doing that as well, and you can pick different options. So how does that do? The main thing about JETSCAPE is that you can run it in PP mode and just compare with the proton baseline. So here are results for the yield as a function of jet radius, as a function of PT. The lines are from JETSCAPE, the data are from CMS. This is the ratio of the JETSCAPE prediction for the jet cross section at R of 0.4 as a function of PT, and everything is divided by PCA. So the one line at 1 is the PCA prediction. Okay, and everything, the data and JETSCAPE are divided by the PCA prediction. This is at small rapidity, this is at larger rapidity, and this is the yield of leading hadrons at all the way up to 100 GeV. Another thing you can look at is the angular distribution of hadrons as I increase the radius away from the axis of the jet. Okay, how much PT is deposited in annular rings around the axis of the jet. And then results in a medium, right? Using, in this case, what we've used matter plus LBT. So matter in the high virtuality phase and LBT in the lower virtuality phase. At 2.76 TeV, at 5 TeV. These are for central and these are for peripheral collisions. I know I'm going a little faster than I should because I'm running out of time. The jet RAA, there are of course issues that most of you know between Atlas and CMS. There's some offset of about 1.5 sigma, but these are our results compared to Atlas. The Q naught here is the scale at which you transition between the high virtuality phase and the lower virtuality phase. So you can see that the effect of that if you vary Q naught from 1, 2, or 3 GeV. This is this is central, semi-central 30-40%, and even more peripheral at 40 to 50%. Okay, it's not perfect, but this is our sort of JETSCAPE out of the box. It hasn't been properly tuned yet with all of the experimental data, but this is how the behavior is just if you turn it on. Also, the R dependence of the RA compared to CMS, I think JETSCAPE does a very good job of explaining the R dependence of the RA for R, say R of 0.2, 0.4, and 1. These are completely parameter-free calculations. And here you already see the offset between the Atlas data in purple and the CMS data in green. More results inside the jet, intra-jet results. These are the angular distribution, the modification of the angular distribution of partons. Sorry, of the PT in annular rings around the axis of the jet. This is the longitudinal distribution or the fragmentation function inside the jet in lead divided by the fragmentation function in PP. We get most of it right, except maybe 1 point at very low Z, and there's more we can talk about. If you have questions about how to fix this, you can add more components in the whole event generator framework. V2 of leading hadrons, V2 of jets. Now we're getting a little lower V2, but maybe there's some more thought that needs to be put into this kind of a calculation. So now we've moved away from leading hadrons and have included all of these other features that you can get from an event generator. But most importantly, what an event generator does is it allows you to put in a Q hat that can have much more dependencies than just depending on temperature. And that, now I go back again to the high energy hadrons and the relationship between RIC and LHC. Okay, so you notice that when you go, we still have that problem that you have two different normalizations between RIC and LHC. And that brings us back to the question of how does the parton see the medium? Okay, at very high scales, the parton sees the medium at a short distance scale in terms of substructure partons. If you look at these two pictures, the substructure partons in both the pictures are the same, but the macroscopic structure is different. So at the scale of the temperature, the two objects are different, but it could be that at the substructure level, they are the same. And I'm showing this to you to illustrate that when you go to higher and higher scales, you start looking at a medium in a very different way than at the medium scale. And this can lead to a reduction in the value of Q hat as you go to higher and higher scales. Which means that when you are in the radiation dominated phase, you see the plasma one way. When you're in the scattering dominated phase, you may see the plasma in a different way. And this is consistent with this idea of coherence that some people have put out recently in the literature. To get that in JETSCAPE, what we've done is we've taken that simple formula, that formula in the HTL formula, and generalized it to add scale dependence and energy dependence. Okay, and what we've done is we've added these coefficients, and this is what I call a data-driven extraction. You compare with data, you run a Bayesian analysis, and then you try to extract what these values of A and C and D are. Okay, again, fitting to the leading hadron RAA, central and peripheral at RIC and at LHC at two temperatures, two energies of the LHC. Remember, this is where we needed a different normalization. But the moment you let the Q hat become a function of virtuality of the parton or energy of the parton, right? You no longer need two different normalizations. It's entirely captured in this dependence. And when you do that and you try to extract back the Q hat, then you get this blue band over here. So first thing you notice is that there's that upward shift, right, that was there in the HTL calculations has gone away. The whole Q hat has now come down a little bit. Okay, it's still somewhat consistent with the LHC result, maybe just still touching the RIC result, but it's kind of saying that if you have a more sophisticated way of understanding jet energy loss, And if you have a more sophisticated dependence of Q hat on not just the temperature, but also on the scale of the parton in the medium, then that will give you a somewhat different value of the effective Q hat. Lastly, and this is something we've been doing outside of JETSCAPE with some of my collaborators, is to try and calculate Q hat directly on the lattice. And this also has many caveats associated with it, which I probably won't have time to get into, where we only look at one scattering in a lattice, and we try to figure out if you write it down, then it's obtained an operator product in a thermal ensemble, and this can be calculated on the lattice. And then we can plunk those results down. So this is the lattice result that we obtained for just a pure gluon-plasma, and the red points are for a 2+1 flavor QCD plasma. So now you're quite far away from the HTL limit, but consistent with the extractions, the data-driven extractions from JETSCAPE. Okay, so that the blue and the red band have overlapped. And it also tells you that we are probably far from the perturbative limit because the green line, which is really the full QCD result in the perturbative calculation, is somewhat away from the lattice calculation and barely touching the data-driven extraction of Q hat. Okay, so with that, I think I'm just within 2 minutes of time, and I'd like to put up my summary. So the transport coefficient Q hat, and I know this is, it doesn't have, this talk probably does not have the kind of grand climax at the end, but I've tried to explain to you, Q hat is a lot more complicated than what one would have first imagined. In all likelihood, it is probably not perturbatively calculable, or at least you have to go to many orders in perturbation theory before you would get a complete result. It probably depends on energy and the scale of the hard parton in addition to depending on temperature. And one obviously needs to go much beyond Q hat to understand the full modification of jets. Jets depend, only the leading hadron depends on Q hat. Jets depend on many other things. And for that, you can either use a series of transport coefficients or some other fundamental property of the medium to get at some underlying momentum distribution function. And Q hat over T cubed at this point from all of these different sources seems to be about 2 ± 1 in the high temperature limit. Now, this is all still preliminary, and many more detailed comparisons at next leading order will have to be carried out to relate the lattice calculation, the HDL calculation, and the phenomenological extractions of Q hat. And that's it. 40, and so thank you for your attention.
Thanks, Abhijit, for such a nice comprehensive talk, and of course highlighting the much complicated this jet medium interaction phenomena than what we think. And now we are open to take few questions. We had some discussion in between, but then we still can take some more. Is it okay, Abhijit?
Yeah, sure, go ahead.
Yeah, so
for me it's morning, right? So I have the whole day.
So if you have question, you can just unmute your mic and ask straight away, or you can also write to chat box if you want.
Can I ask one question?
Yes, sure.
So, sir, thank you very much for this beautiful talk. So, I have just one question that you have told 3 major phases of jet. One is high virtuality, high energy. Another one is low virtuality, low energy. And, and another one is high energy and low virtuality. And you have introduced 2 transport coefficients, Q hat and E hat. So which one will be more efficient to explain all these 3 phases?
So mostly Q. Okay, so if you want to look at the whole jet, Q hat is most important in the high energy, high virtuality phase. Okay. Q hat is also the most important thing in the low virtuality, high energy phase. But in the last phase, right, which is the low energy and low virtuality, okay, this phase, this is where sort of the outer end of the jet is. Here it is not just Q hat. Here it is Q hat. It could be drag. Let me just jump ahead. Is there a way I can go faster than this? So if you go to that phase, low virtuality, low energy phase, then all of these transport coefficients, Q hat, E hat, and these softer ones, which tell you how the energy deposited by the jet is then redistributed in medium, they play a role. So for the hardest part of the jet, high virtuality, high energy, or low virtuality and high energy, it's mostly Q hat dominated. But the moment you now go to low energy, low virtuality, it's a whole bunch of new transport coefficients. Q hat, it's E hat, and it's whatever you use for this. And so what I was telling you here is that what we use is this mechanism called recoil, which is mostly energy momentum conservation. You hit a parton in medium, you see how that parton now becomes part of the jet, and then you have to subtract the energy of the incoming parton. And there are many ways of doing that. It's not the only way. I hope that answered your question.
Yes, okay, sir. Thank you.
She was Devjani, and now anyone else? So, if you can also tell your name, please.
Hello, sir. Can I ask you a question?
Yes.
Okay. Okay. My name is Revolution, and I'm from IIT Indore. So first of all, this is a very good talk and presentation. So actually, my question is based is a basic question, and I have one more question that on imagination. So my first question is, as I understand, jets depend on parton fragmentation. So how it is depend on leading particle? I didn't understand. So can you explain it?
So the leading particle is only one part of the jet. Okay, so when you say jet, you mean a whole collection of partons, which eventually will become a collection of hadrons. And there are many ways you can study this, right? You can look at the total cross-section of jets within some angular range. You could look at how the partons or hadrons are distributed, or how the energy is distributed in angle away from the axis. You can look at how the partons are distributed in the longitudinal momentum distribution of the jet. Or you could look at just the highest energy hadrons in the jet. These are all different ways of looking at a jet, different parts of the jet.
Well, actually, my question is little different. Like if jet is segmenting from, let's suppose, a parton Q, and then it can go after hadronization, it can go in any hadron. So is it depend in which hadron it will go, or it just depend on the parton in which the jet fragment?
I'm not sure I understand your question, and also there's a lot of interference, so I'm not sure I heard everything.
Please switch out your microphone after asking the question, because okay, maybe what he might have asked is that when a parton fragments, now all the properties that we are talking about, does it depend on the parton, or does it depend the way it fragments, that means on the hadron? That's what I understood.
Yes, sir. Yes.
So
Ravindra, you just exactly. Okay.
yeah, okay. So I think that the point is that when a parton fragments, that depends entirely on the parton. Okay. what its energy is, what its off-shellness is, and if it's inside the medium, it depends on the medium in which it's going. Okay, the hadrons are an after the fact, right? So once you have a parton shower that has developed, right? Some part of it is in the medium, some part of it is outside. The hadron shower that happens at the end after fragmentation depends on the parton shower. Okay, so the structure of the parton shower determines the structure of the hadron shower, and not vice versa. I don't know if that answered the question.
Yes, it is answered, and thank you for this question. And I have one more question. I just imagination, like if there is rotation around jet axis, so it also affects the broadening of jet. So is it
Rotation of what? Rotation of
the associated particles inside the jet around jet axis?
Rotation of what? Are they rotating those particles, or you are rotating for your analysis? What do you mean by rotation?
yeah.
Actually, I was asking, like in jet, all the particles inside the jet, if they are rotating around the jet axis, then it should be effect on jet broadening. And same if
Yeah, so they're not rotating. They're not rotating like that. You could have some net angular momentum if you add up all the angular momentum of all the particles in the jet, but it's not rotating like this. Okay, that's not happening. Okay, they're all. It really is like a cascade where you just decay, and then you have all these particles going out. It's not. Once they have, the most important thing is once they have split off from the jet, they are no longer sort of still correlated with all the other particles. Rotation means there's some kind of correlation, right? So this one has to know what the other one is so that they can rotate like this. But this is really a question of decay after decay after decay after decay, and every decay they become decorrelated from the rest of the particles. So no, there is no rotation like that.
Okay, thank you.
Abhijit, can I ask something? Your slide number
Yes, yes.
17. 17.
17.
Yeah. So that conceptually, I just not very much clear that you said that non-monotonic behavior, maybe on 17, 18 or something like that.
Yes.
So
yes.
here. So what it exactly physically means? So that means you have a confinement or deconfinement transition, or
so this is the deconfined region up here, and this is the confined region. I am not proposing that this is true. Okay, I am against this idea, but many others have proposed this as a case. What they are saying is that when you look at Q hat over K cubed, it doesn't just go down from the large value in the deconfined phase to a small value in the confined phase. It actually goes through it goes up and then goes down. And so this is mostly being proposed by Miklos Jolassi. And the idea is that there could be monopoles at the location of the transition, and monopoles means there are more regions where the jet could scatter off. And that would lead to this rise. And I don't agree with that. I'm just saying that it's probably scale dependence. At least that's what we think.
I just want to understand that this okay, you don't agree with this idea, but the thing is that what exactly idea is that is this happening inside the jet structure, or it is independent of that?
It's in the medium.
In the medium.
It's in the medium.
So
the medium just at transition point, there are many new scattering centers in the medium.
So it means just at initial type collision, or maybe in the after initial condition, I mean after the collision, initial condition of initial stage of collision. So it is like
No,
you
so-
have to reach the freeze out before freeze out. This is happening.
Before result. So you collide, okay, you make Quark-Gluon-Plasma, and if you look out radially, you find that it's cooling down, and then there is a hadronic plasma, okay, and of course this is continuously evolving, right? So the plasma, the QGP expands and then contracts back in and turns into. But if you look at the transition region between Quark-Gluon-Plasma and hadronic plasma, what this idea says is that in that tiny region there is going to be some high dense structure, right, where the jet will come and get extra suppression, and it goes through that region. There'll be more objects in this region that the jet will scatter off.
The idea like Jepside suppression type.
No, no. I mean, in side suppression, that can happen.
You wanted to just verify that whether this is a QGP is formed. So in the QGP medium, so maybe jet will be suppressed. Like idea is like that, or like Jepside also like suppressed. So is it like that, or is it different from that?
So jets are suppressed similar to the way that the JSI is suppressed. This is saying is that near the transition between the plasma QGP and the hadronic plasma, there may be extra suppression.
Okay.
In that.
So, but this has not been verified. I mean, this idea has not been verified in experimentally, I guess.
Other than these 2 points.
Yeah. Oh.
So it depends on what you think these 2 points mean.
Yeah. Okay. But there is a concept like transition from very low energy to high energy, like 8 GeV to that more than 8 GeV. There is a critical point. Is it the idea something like that? There is a discontinuity to like monopole, not monopole.
Yes. So people have connected this to the critical point that said when you get close to the critical point, you know that like if you look at viscosity, right? There's a dip in the viscosity just as you get to near the critical point. So yes, this idea of the monopoles is related to that by saying that it's not near the critical, it's not at the critical point, but maybe it's near the critical point where you see some hump, and if you go to if you could go near the critical point, then this would become much bigger.
Okay, but you don't support this idea.
I don't know.
Okay. Thank you very much.
Yeah, my view on this is always, if you have a simpler explanation and a more exotic explanation for the same property, then I will always pick the simpler explanation.
Thank you.
Do we have more questions? Prof, is there any question? Is there any question from there?
Okay, maybe Siddharth, yeah, go ahead.
Hello, sir. There is a question in chat box. Hello, sir.
Sir, I have a basic question that when jet is strike the target, then either it modify the structure of target or not. If yes, then what parameters are modified? Yes, the jet does in fact modify the target. That's what I was trying to show here, that both get modified. Okay, Let's see if I can get out of this simulation. Here we go. Can you still see that the simulation? Can you still see the talk? I don't know.
Yes, yes, yes.
So when you have a jet and it's of course it's produced inside the Quark-Gluon-Plasma, and the Quark-Gluon-Plasma is also the target. The jet is modified. That means energy has been taken out of the jet and it has gone into the medium. Momentum has come out of the jet and gone into the medium, but the medium is also modified. Okay, both happen. Jet is modified and medium is modified by energy momentum conservation. What parameters are modified? Okay, so for the jet, it is the momentum structure that is changed, and for the medium, it's the I'd say that if you're using fluid dynamics, then you have some hot spots produced where the jet went through the medium. And those become sources of hydrodynamic flow.
I think, Priyanka, does that answer your question? Okay, so maybe
yes, sir. Yes, sir. I got the answer. Thank you, sir.
okay, so maybe I can ask one question. So, Abhijit, what do you think about the effect of magnetic field on these transport coefficients? Do you?
You mean the electromagnetic field? On Q hat, I don't think there is much of an effect. Purely because the jet is at a much higher energy scale, and so I don't, for the magnetic field to work, two things have to happen. So if you look at this CME, like color magnetic effect, whatever it is, right? Chiral magnetic effect, that happens very early in the collision, right? Just when the two nuclei are passing each other, right? That's when you have maximum magnetic field. Most of the jet quenching happens later, right? And so that's why I think that maybe there is not much of an effect on jet quenching, because jet quenching happens sort of later in the plasma, once the plasma is fully formed.
But if that magnetic field stays for some time when this phenomena of jet quenching is happening, then there could be some effect, right? If
you have that, if you have this idea, I know this idea of eddy currents, right? So you have quarks are being produced and they maintain the magnetic field somehow. That could have some effect, but it would be a correction, I think, on top of what we have right now. That's my sense. It'd be I can't see it being an enormous effect, because most of the jets are, look, there's so many things, right? So there are particles in the medium, the jet scatters of them. But then the particles are moving because of flow, just regular flow. And that changes the Q hat a little bit, because now you have a flow correction. And now you're saying on top of the flow, there's also this magnetic field, right? Which is another correction on what you have as the momentum distribution of partons. So that could have, it's a correction on top of a correction.
okay. So
Okay, Siddharth, I think you may close it now. It's already 7:30.
Okay. Okay, so
Understand more question, of course.
yeah, if you have more questions, then of course you can send to Abhijit through email, or to me, I can communicate to him. And thank everyone for joining, and especially to Abhijit for finding time in the early morning. Okay, we will have you sometime in future again. So thank you so much.
Yes, I look forward to that. This is my first, I've given many seminars in India, but this is the first one I've given in India, but not in India.
That's good. Yeah, that's good.
Okay. All right, thank you.
Okay, thank you. Thank you, everyone.
Talk to you later. Bye.
Bye. Bye.